Log on, tune in, find out. Another good idea from Cambridge.
Alexis Boukouvalas from Aston University. This talk somehow is anticipating a little bit of next week's conference about computer experiments. Alexis will be talking about optimal design under heteroscedasticity for Gaussian processes emulators with replicated observation.
Thanks, Hugo. And I would also like to take the opportunity to thank the organizers for a very nice conference. Okay, so yes, I will be talking about optimal design for Gaussian processes emulators. This is joint work with Dan Comfort, who is was my supervisor at the university, and Milan Steklik, who's at the University of Linz in Austria. So the overview of this talk, I'll set up the context where this work is taking place. I'll describe what heteroscedastic means and what these Gaussian process models are, what choices we have made. And then I'll talk about how we do design for this type of models. And then I'll have a set of simulation experiments to demonstrate certain aspects of these models. So I'll talk about synthetic data, and then also about have a short discussion on the monotonicity, and it'll become clear what I mean, of the Fisher design criterion. And then we have a short application to a systems biology simulator. I will finish with some conclusions and future work. Okay, so emulation. What is emulation? So this is part of this MUCM project that I'm part of, which is managing uncertain complex models. So broadly speaking, the context is that you have a very expensive to run piece of code, which we call a simulator. So these are termed computer experiments. And assuming this is very expensive to run, people have proposed to build a statistical approximation to it. And this is called the emulator. And typically, a Gaussian process is used as this approximation. So most of the literature you see in computer experiments has a strong assumption that the simulator is deterministic. Okay, so having replicated observations makes no sense in that context, for example. In terms of design, the standard optimal design theory typically assumes independent homoscedastic errors. That's a common set of assumptions. People have already extended to the heteroscedastic case. So heteroscedastic means the inputs are input dependent. So I have a reference to get, if anybody's interested, to get you started. And also people have extended to the correlated setup. And I particularly would like to point this paper by Zhu and Stein in 2005 in JSPI, because our work is built on top of their work. And just a few caveats. All the nice optimal design theory, when you move to the correlated error case, a lot of things break down. The general equivalence theorem doesn't hold. Nice properties such as the additivity of the information matrix do not hold. So there are multiple caveats you have to watch out for. I don't need that. Okay. Okay. So what this work is about is we basically work with heteroscedastic Gaussian processes with a nugget effect, and we introduce a type of Gaussian process to do the heteroscedastic bit, and we choose it with in mind to do optimal design. And then we propose a method to optimally learn the parameters of such models, and this is using the Fisher information, and this builds upon, as I said, the Zhu and Stein work, which extends this work basically to the heteroscedastic case. And throughout this work, we explicitly want to consider replicated observations in both the model inference and the design state. I'm not used to this thing. Okay, so for people who don't know, I have a slide what a Gaussian process is. It's an example of a stochastic process. So you can think of it as a prior over functions. Formally speaking, it's any collection of random variables, which is infinite. But if you take any finite subset and it has a joint Gaussian distribution, this defines a Gaussian process. And Gaussian processes are defined by a mean and a covariance function, the specification of which allows you to incorporate your prior beliefs of what the function should be doing. So you can define things such as smoothness and differentiability. And here I have an example. That's nice red sine curve, and I observe it at 4 blue points there with a bit of observational noise. You see they're not on the line. Then I fit a Gaussian process, so that's the mean and that's 2 standard deviations. And I fit a 0 mean Gaussian process with a squared exponential kernel and a nugget effect. So so they're very nice to use and have a lot of nice tractability properties. That's why people use them. Okay, so as I said, most of the work published for computer experiments assumes a deterministic simulator. So we typically can represent it in y equals f of x. X represents the inputs to the simulator, y represents the outputs, or some summary of these, and f here represents the mapping imposed by the simulator evaluation. So when you build your emulator, you put a Gaussian process where you have observed the simulator, and the probabilistic nature of the Gaussian process in this case arises only from the approximation to the simulator due to having finite number of simulator runs. So at the observations you interpolate perfectly, you don't have a nugget effect as is commonly known, and your uncertainty comes from when you're predicting away from your training point. Okay. So our work is on stochastic simulators. So that here the simulator, if you run it multiple times at the same set of parameters, will give you different outputs, gives you a distribution. And in this case, in addition to the previous source of uncertainty, you also have uncertainty due to the stochasticity of the simulator. And our observation model, we can write it as y, depending the response on xi, is some underlying function, and we choose to represent the heteroscedastic part as being input dependent. That's a realistic assumption. But we still assume that the stochastic output at a point is distributed as a Gaussian. Okay, so if you want to do a Gaussian process for the heteroscedastic case, what you can do is there are multiple approaches. So we've considered two. One is I call it a coupled system of Gaussian processes. So you essentially have one Gaussian process taking care of the variance, which is input dependent, and another Gaussian process predicting jointly the mean and the variance, and they're actually coupled together. And you can write this down. It's quite simple, but inference is quite tricky because it's no longer tractable. So in 1998, Goldberg et al. Solved the inference problem doing MCMC. This is very slow. The Kersting and his collaborators in 2007 proposed a very crude simplification where you only use the most likely, so the mean prediction of the variance Gaussian process, and this makes things very fast, but you don't account for the extra uncertainty there. And just very recently, Lazaro and Titias proposed a variational approach, which is only about 2 times more expensive than the most likely and gives you a fuller accounting of the uncertainty. And we have taken this type of model and we have extended it to utilize repeated observations. I don't talk about this here because this type of model is too difficult to use for optimal design. So a much simpler model is we call the joint likelihood model. We basically drop the Gaussian process for the variance and we substitute a parametric deterministic variance model. And now the optimization of the mean and variance model parameters can proceed jointly. You can write a single likelihood and things are much simpler and your optimal design calculations are tractable. So, and again, we can do efficient inference with replicated observations in this context. Okay, so just a side note, why all this talk about replicated observations? I just want to say a couple of points that Gaussian processes, when you have points very close to each other, you can have numerical problems, and also when you have moderate to large number of training points, inference time can become a major headache. And a very simple way of solving such a problem is to consider replicated observations. So when I'm talking about explicitly consider replicated observations, you assume that the errors are Gaussian, and basically you only use the mean and the sample variance at each point. You don't use the raw observations. Okay. So the joint likelihood model. So what this means is we have a deterministic variance. parametric model, and typically the prior can be written in this way. So because our focus, and I should have mentioned that before, is on the estimation of the kernel parameters, not the mean parameters. So just like in Zuenstein, we assume a 0 mean prior for the Gaussian process, and the kappa theta is your standard Gaussian process kernel. And then we have a diagonal matrix, which basically the exponent here is to make sure we predict positive variances. And we have a function f here, which depends on the inputs and some parameters beta, and it predicts the input dependent variance. And the p matrix here has to do with the number of replicates at each point to keep things consistent. And you can, as I said, you can write down the likelihood for this model. And the red term, for people who are familiar with Gaussian processes, is just what you get normally with a Gaussian process. And the R matrix here is this diagonal that I have here. The blue term here is an extra term that you get that has to do with the existence of replicated observations. So SI squared here is just a sample variance. So you can write down a joint likelihood here. Just a couple of examples of models we have considered for the variance. One we call it fixed basis variance model, and here the log variance function is modeled as a linear in the parameters regression using a set of fixed basis functions. So you can write it like that. H here is a set of fixed basis functions with known parameters, and beta is your parameters of interest. Now the latent kernel model is an alternative we can use. It's still deterministic, I have to stress, but because you could be in high dimensions, you may want a non-parametric method. So here examples could be polynomial basis or radial basis functions, which are local basis. But here we actually use a kernel, but it's still a deterministic function. Okay, so nothing much changes. Basically, the point of this slide is you can use a large variety of models for your variance. Just a short picture on applied these three models, the coupled model, latent kernel, and quadratic polynomial here for the variance, and fitting it to this black line is the true model, and the blue dots here are the observations that you see, 4 at each point. The coupled model has the best fit. The latent kernel here, these green diamonds, are the basis where you are centered, and the quadratic is a global basis, so you don't need anything. So we can clearly see the coupled model in this case has the best fit, and this is in general true as long as you have enough data. The problem with the coupled model is it gives you a lot of freedom, so it's very easy to overfit if you're not careful. So these, in addition to being simpler to do the inference, these models are more restrictive. Okay, so now we'll talk about design, which is the main focus of this talk. So our focus, as I said again, is to minimize kernel parameter uncertainty. We haven't considered trend parameters. Question could be, why don't you think about minimizing the predictive variance? Because this is the thing that's actually quite often of interest. The answer is that I'm aware all such methods assume the parameters are known of the kernel or use approximate values for this. So we envisage the optimal kind of designs here. We can be effectively used as preliminary design or as part of a hybrid criterion. An example is Zuenstein 2006 paper to help you narrow down your parameters, so to minimize the variance of your parameter estimates before looking at minimizing the predictive variance. Okay. So this is just what do we do for optimal design. As I said, it's designed to minimize the parameter uncertainty. This naturally leads to de-optimality, and we minimize the Fisher information. The Fisher information is defined as the expectation with respect to the second derivative of the likelihood, and because we've chosen to have a nice simple model for the variance, and the Gaussian process is already tractable, the joint thing still remains tractable. And this is the analytical solution. So again, this is just a more expanded version of the previous definition of what Fisher information is. The joint likelihood model that I described previously, you can analytically calculate this. It's basically composed of two sets of terms. The second term, f of n, is the half of the trace of this product of covariance matrices. And basically, this is what is in Zuenstein 2006. 2005, sorry. And this is what you would get if you just had this bog standard Gaussian process. But because we are also explicitly considering replicated observations, we have an extra term here that depends on the variance model and the number of replicates. So you can see if the number of replicates is 1, this disappears and you go back to what you had for Gaussian processes, normal Gaussian processes. So it's nice and tractable. Okay, so that's our basic way of doing the design. That's our design criterion. I'm going to present now some experiments. We have, following again the approach in the literature by Zhu and Stein, to demonstrate the properties of these designs, we sample from a Gaussian process with known parameters. This is our synthetic experiment. And then we fit, using maximum likelihood inference, a Gaussian process with exactly the same covariance. So there is no mismatch here. It's an artificial example. And we compare different designs to see the properties. And we compute the parameters errors, and we do this a lot. Okay, so these are the types of designs we compare to see the effect on parameter estimation. The first and the last are what locally optimal designs. The first here is computed using a greedy optimization algorithm. We just start with a single point and add the next point that maximizes your information. And the simulated annealing, it was actually described in the previous talk. So we also have some space filling designs. In computer experiments, it's very often that people use maximin. This is a maximin Latin hypercube. We also look at a maximin Latin hypercube with replicated observations everywhere, so 2 everywhere. And we also have a grid design for reference. So comparing all these designs, I should have talked. We're using a latent kernel variance model here with 3 bases. I should have said that. And actually, this is interesting. The bases are actually located at these points, 0, 0, half, half, and 1, 1. So you can see the optimal designs put a lot of points around there. The variance model, what it looks like, so you have an idea. This is the kind of surface, and this is the main. Yeah, this is the main result. Okay, so this has to do what we plot here, and I have a few of these plots, so I need to explain it. This is the Fisher information here, so it's the log determinant of the Fisher information matrix, and over here it's the log determinant of the empirical covariance matrix of the maximum likelihood estimation of the parameters. So ideally, what you would want for all the designs, you want the Fisher information to correspond exactly to this quantity, because asymptotically this is what you're trying to get to. And we see a relationship here. So these L and Z are the single replicate space filling designs, the maximum Latin hypercube, and the grid design. These are the replicate grid and replicate maximum Latin hypercube, and this is the simulated annealing and the grid design. So what we notice here is that they're not on the line, and actually, unlike previous work, there is no strict monotonicity. Basically, the designs for the single replicate are much worse than what we would expect by looking at the Fisher information. Okay, so when you just have points with single replicates, you have the approximation of the Fisher information to the maximum likelihood breaks. Okay. And where this is a summary of your joint parameter estimation error. So where are these errors coming from? Actually, if you look, because we have 2 sets of parameters, we have the parameters inside the kernel, so the length scale and process variance, etc. We also have the parameters of the variance model itself, and if we look at just those, actually, we see that the gradient simulated annealing have the smallest errors. This is a kind of RMSE on the parameters, because we know the true parameters. The replicated grid and the replicated maximum Latin hypercube have the second smallest errors, and the single replicate designs have the highest errors. So the differences between the designs come out when you're looking specifically at the heteroscedastic variance model, the parameters for that. Okay, I won't talk about this much. Just a caveat. I just wanted to broadcast this kind of advertise. There's an approach published in Technometrics by Bastos and O'Hagan. Actually, I think the date is wrong. I have the reference at the end. When you're doing validation of a Gaussian process, by using the Mahalanobis error, you can decompose it into what's called uncorrelated errors. So essentially you take a Cholesky decomposition of the Mahalanobis error, and looking at this decomposition can tell you a lot of where the source of your validation errors come from. And here I'm actually comparing a grid design with a simulated annealing optimal design. I won't tell you any of the details, but what you want to see is, kind of spread nicely uniformly like this. If you see structure in the error like this, depending on the structure, it can tell you where your parameter estimation errors lie. So in this case, actually, this kind of structure where the pivot order here on the bottom tells you the kind of distances where the errors happen. So the points here are basically very close to each other. So you would suspect that you have the length scale here wrong. If the errors were here, one of your other assumptions, like the process variance or the variance model parameters, you were getting wrong. So it's a very useful diagnostic. So I would recommend its usage. Okay, so we saw previously that the monotonicity of the Fisher information was broken with respect. So what this tells us is, strictly speaking, in the general space, it's not actually a valid design criterion. So we look at two types of monotonicity now, trying to drill down. And basically what we have here is a set of designs without replicates and a set of designs with a lot of replicates, and we increase the design size. So as you increase the design size for 3 different noise levels, we see that the monotonicity holds. So with respect to the design size, and we have some theoretical results for specific cases, for an OU kernel, etc., then this monotonicity with respect to the design size holds. But the more important type of monotonicity is with the with the parameter covariance of the maximum likelihood estimation. And we did a different experiment where we have kind of a grid design, very dense, and we take a point out and we put it back as a replicate. So this plot here is again the Fisher formation with respect to the log determinant. And as you increase the ratio of replicated points, your approximation of the Fisher information to the log determinant becomes better and better. You can see it goes towards the diagonal. So single replicate designs are not approximated well, and the monotonicity doesn't strictly hold, but the approximation becomes better and better the more replicated observations you have. So these are empirical results. Okay, and a short study. We looked at the systems biology prokaryotic autoregulatory network. This is a very simple model. It's minimal in terms of biological detail, but contains many of the interesting features of an autoregulatory feedback network. And I will give the reference. It's a book on systems biology by Darren Wilkinson from University of Newcastle. And this particular model contains 8 reactions with 5 reactants. So this is actually the quantities of interest are to do inference on the rate parameters, so K1 to 8. But this is quite difficult. It's an 8-dimensional space. So for this example, we restrict our attention to K6 and K7 reaction parameters. So we turn this into a 2-dimensional problem. The domain region for K6 is between 0 and 7, and K7 is 0.5 and 0.4. Okay, these numbers don't tell you anything, but basically they are from the literature. And all the other parameters are fixed to some nominal values. The initial, for your reference, the initial number of molecules has to be set as well. And then it's a dynamic system. You turn the crank and you use something called the Gillespie algorithm, and you can do exact simulation from this type of networks. And we have selected to use this as our simulator at a specific time point, t equals 18, for your reference. So the emulator we have chosen to use for this small case study is a zero mean Mattern covariance with fixed differentiability 5/2. So basically only the length scale parameter and the process variance are free here. And for the variance model, we have used a 9-point latent kernel arranged on a grid. So this will become clear. And we choose to do a local design. Now we have done Bayesian design here, but it just gets more complicated and more expensive. So I'll present a local design, which we assume a short length scale process. Local design, you have to fix the thetas, and a high noise to signal ratio. So we do local design, and these are the optimal designs for 3 different design sizes. And you can clearly see structure here. And actually the points of the optimal design here, these were done using greedy optimization. The points correspond to the locations of the latent points of the latent kernel variance model. So they are actually the latent points, the RBF network basically that you have, is the points are spread in this way. So you have a design with a lot of replicates. Okay, so this, again, same type of plot, Fisher information with respect to the log determinant of the empirical covariance of the maximum likelihood estimates for three different design sizes. So the squares here are 30-point designs, the 100 points are the diamonds, and the 200 points are the circles. Okay, so you become more certain as the design size increases, so that's reasonable. And we don't consider the single replicate designs here, so we consider the replicate grid design and the replicate maximum lightning hypercube and the optimal design, which we depict by F for Fisher design. And the thing here is when we reduce and we only essentially consider designs with only replicated observations, there is a very nice correspondence, at least in this example. So the Fisher information is a good predictor in this case of the maximum likelihood covariance. Want to say anything else? No. Okay, conclusions. So the model we have used is a heteroscedastic for heteroscedastic emulation. I've shown you a variety of different complexities for the model. We've chosen to use a very simple heteroscedastic Gaussian process model, and this allows for optimal design calculation. In combination with a discrepancy model and real-world observations, this method could facilitate the efficient statistical calibration of stochastic simulators. Basically what this means is you can take this approach and then all the literature has already been published, how to do calibration, etc., could be applied to this type of model. In terms of experimental design, we have used Fisher information to minimize kernel parameter estimation variance. We have been utilizing replicated observations directly, and we have found them to be very beneficial for stochastic emulation. And I just mentioned this. The Mahalanobis-based validation error reflects the lower parameter estimation error and can help you pinpoint where your problems are. Okay, open questions. So, in terms of model flexibility, we've been modeling the first two moments, and this may be too restrictive in some applications. So there are a variety of non-parametric density methods we could apply. Something from spatial statistics is called indicator kriging, or copulas, and basically you can model any kind of distribution, but you need a lot more data. In terms of experimental design, the use of replicated observations improves the Fisher approximation, but we don't really know why this is the case. Is it because what actually happens as you add more replicated observations? Your estimation of the nugget parameters, the variance model parameters, is better. But is this, we would like to learn more about exactly this approximation error. The effect of the Fisher designs on parameter posterior, so when you're doing Bayesian inference, so we started looking at that. And as you would expect, since you minimize parameter error, you would expect your prediction error, since in Bayesian inference, your prediction error also takes into account the uncertainty around your parameters. You would expect to have lower, basically more concentrated posterior around your parameters, and hence lower prediction error when you're doing Bayesian inference. And in our limited examples, we have seen this. One thing I haven't talked about is we do a candidate set, and that's the way we do our optimization. It's a discrete optimization scheme, and this suffers from the curse of dimensionality. So as you start considering higher and higher dimensional input spaces, design spaces, the candidate size you require blows up, and your optimization time blows up. So we need solutions here. You could very easily incorporate trend parameter estimation, and people have already done this for other scenarios. And we would like to also consider extensions to the adaptive context when you do things sequentially and you get observations, and other models, example quantile regression. And I will leave you with a list of references. So for Gaussian processes, for optimal design, and the system biology case study. Thank you very much.
There is time for one or two questions now. Steve.
So can you go back one slide? The first point on the design, that if it's the main advantage of the replicate observations is to identify nugget parameters, you would expect to be able to do that with rather few replicates. So have you considered designs where you just replicate a few points rather than replicating the whole design?
Yes, that's, I think, true if you have a homoscedastic case, but if you have a very complex variance response, you need to learn kind of the surface, I would expect. And you need to disambiguate the two sources of uncertainty. That's my intuition, but we would like to understand this more. And another thing I haven't really talked about is when you have very highly clustered designs, sometimes your error on your length scale can increase, but this is compensated by having a much lower error on the negative parameter. So,
There are no further questions. Let's just thank Lexi again.